All right, so from today we start the discussions related to a new semiconductor device, bipolar junction transistors. And so today's lecture will be a introductory lecture. We'll go over concepts, many of which you're already familiar with. All right, so that's the little bit of history here. First point contact transistor, invented by Bardeen and Brattain, 1947. And so this was basically two contacts made to a piece of semiconductor, and it provided amplification, and that invention marked the birth of modern day electronics here. These are the three people you're familiar with who were involved in the invention. As I've written here, the point contact transistor was actually invented by only Bardeen and Brattain, these two. And the junction transistor, which we are going to talk about, two junctions, and which was conceptualized by Shockley, and this was in 1951. The junction transistor that we are going to talk about. Okay. All right. So as a reminder, a transistor, if you recall, we said that if you take a three-terminal device, we had discussed this earlier. If you have a three-terminal device in a transistor, what you're looking for is that at the output port here, we have output current, and at the input port, you have input voltage here. What we are looking for is a device in which the current, output current, is much more sensitive to the input voltage V in, and as compared to its sensitivity to V naught here. Right? So that's what we are looking for. Ideally, I naught would respond to V in only and will not respond to V naught. It's independent of V naught. That's what we are looking for in a transistor. And so the ideal transistor then, in some sense, is given over here. Is so output response to input voltage here, GMVI here, and we call it GM because the current is related to voltage applied across a separate pair of terminals here, GMVI here, and that's what it is. That it only responds to input voltage, doesn't respond to output voltage here, independent of output voltage here. When you look at it from the input side, the applied voltage goes into your transistor and affects only the output current. There's hardly any input current. All right, and I'm calling it ideal transistor because when you use it in an amplifier, for example, you will get a circuit like this will give you infinite input impedance. And if GM and there is infinite output resistance also. If you note that in a practical case, you would think of a current source always in parallel with a resistor, and therefore we have infinite output resistance also. And it's a perfectly linear device. We are saying I naught is related to VI through this GM here, and we are assuming GM is constant. So it's a perfectly linear device here. All right. So what we are saying is I naught is linearly related to VI, and I naught is independent of any output voltage that you apply here, right? It only depends on the input voltage here, VI1, VI2, VI3. So these are the characteristics that we are looking for, right? A practical transistor, of course, would try to approximate such a characteristics over a certain range. It's not going to yield devices like this here, okay? So one way of looking at a transistor then is basically a voltage control current source. Right, so this is a dependent current source and is controlled by a voltage here. So that's the feature that you're looking for, a voltage control current source. All right, and we know that if you have an element like this here, you can very easily make an amplifier. So apply the voltage that you want to be amplified, connect a load, take this transistor here, replace it by its equivalent circuit here, very simple equivalent circuit here, and it's straightforward to see the gain is equal to minus GM times RL, and all you need to do is connect for a given GM, connect an RL of sufficient magnitude, and therefore you get a voltage gain. And we can also see that you'll get a power gain because there's hardly any power going in because of the open circuit here, so you're not drawing any power from the signal source, and of course you're delivering power to the load here, so you have a power gain also, right? So the real test for amplification, as I've emphasized, is not that voltage amplification, but you must get power amplification, okay? All right, so with this background, then let's look at our bipolar junction transistor. So this is a schematic that you're familiar with. We have a bipolar transistor, which we call as NPN. emitter, it is made up of 3 terminals here, emitter, base, and collector. Emitter is N, base is P, and N here. And this is the diagram that we have here, a schematic of the symbol of the NPN bipolar transistor. And similarly, we have a complementary transistor, which is PNP, where emitter is P, base is N, and collector is P also. And the schematic of the symbol here is shown, right? So base, emitter, and collector here. So that we have 2 transistors here. Most of our discussion would be related to NPN, but then similar equations, similar identical concepts hold for PNP as well. Okay. All right. Okay, so this is a simplified view that we draw, one-dimensional view, and we say emitter is here. We stick a terminal to the base over here, and then we say collector is over here. So this is a simplified schematic. The actual cross-section of a bipolar transistor may look more like this here. This is also simplified, but it may look more like this here. So note what we have is an N plus region, which is we'll see why we require. We've seen it also that this is the emitter region here, N plus, and this is the base region here, and then you have a collector region here, which is N also. Underneath we have an N plus, and then the substrate is a p-type silicon here. Substrate is a p-type silicon, and all the contacts are made at the top here. That's a emitter here, base here, and collector here, right? And so this is how a transistor may actually look like. And if you note, this is what you see here is that the emitter has a certain length of the emitter here, and the thickness of the emitter region here. These are usually very small. Similarly, thickness of the base is usually very small here. And this N plus layer is needed because note that as the electrons are injected, they travel across the base, reach the collector here, but the contact is over here, so the current has to travel all the way to the contact here. And you don't want series resistance here, so as the electrons travel, they will see a lot of resistance, and therefore you put a N plus layer here. So the electrons, once they enter the collector, they go into the N plus. It provides a low resistance path directly here, and then it goes up here. Also keep in mind, the diagram is not drawn to scale in the sense that the lateral dimensions are in micron. For example, my emitter length could be 1 micron, and then from here to here I could have 5 micron, and from here to here I could have 10 micron, right? So lateral dimensions are in micron, and vertical dimensions are 1000 angstrom, 100 nanometer, right? So this is 100 nanometer here. This could be 100 nanometer here. Collector itself could be 200 nanometer here, right? So the lateral dimensions are when I'm talking about the need for an N plus is because the lateral dimensions are large, right? So as the electron travels, say 20 micron length here, and collector, this N region doping is less, let's say 10 to the power 16 or 5 times 10 to the power 16. So what it sees is a resistance. And you want your transistor's characteristics to be determined by the junction properties, right? Rather than by a series resistance. That's not what you're looking for. You're looking for a transistor and not a resistor. So that's why you have to minimize any series resistance in your device, and that's why you put your N plus here, so that you don't see a large series resistance. You see an N plus, and then it goes up here. Going up, remember the dimensions again are very small. So this resistance is there, but it's not as large as lateral resistance. So that's what you're trying to minimize through N plus here. Okay, and you can see also a typical doping levels. 10 to the power 19, we make it N plus here. Base maybe 10 to the power 17. Collector is often lower than the base here. Couple of times 10 to the power 16 here. And typical thicknesses are also given here. 1000 angstrom, as I said, emitter thickness. Base maybe 1000, 2000. These vary depending on the design of the bipolar transistor. These vary. And also from this diagram, one can see that BJT is not symmetric. Note that emitter is N plus here, and the collector is simply N. Emitter is of smaller dimension. The collector is much larger dimension here. So BJT is not symmetric. Emitter and collector simply cannot be interchanged and expect that the characteristics will remain the same here. Okay. All right, so the schematic that we had drawn here, this NPN, where does it come from? Well, it basically reflects this particular region here, the region between the two dotted lines here. The region between is, I think, on the darker side there. I don't know whether you can see the dotted lines. No? Dotted lines are there. All right, so these are the two dotted lines here, and it is between these two regions here. That's where that's where the action takes place here. You have an N plus, you have a P, N, and all that. The rest of the region here, for example, this is needed to provide a contact to the base. And similarly, all this region here is needed to provide a contact to this N region here. So all that are, in some sense, support regions for providing contacts. The real action where the transistor behavior comes from is shown between these two dotted lines here. So if I leave that these extra regions for a moment, then this is the structure that we obtain. We have an N plus, we have a P here, we have an N, and we have an N plus, and then again a P here. Now, P is a substrate. It doesn't play much of a role. As I said, the transistor is only till here. So what we do is, in a simplified schematic, we leave this P out. We leave this P out, and this N plus only provides a contact. So we leave this N plus out also, and we simply draw N plus P, N, and we say there's a contact here, keeping in mind that the contact is actually provided by N plus and then eventually here. But then we say there's a contact here. And base, we know that there's a base provides a contact here through this region here, but we simply draw and put a contact here. So understand what this contact means. It doesn't mean that I have something stuck to the side. It means that the contact is over here, right? And this region plus all this P-type region is what we are representing here. And similarly, N plus, we put a contact here. So this is how we arrive at our simplified a one-dimensional view of a NPN transistor here. But this is how your transistor actually looks like here. Okay. All right, and this would be a top view. This is a cross-sectional view, and this is a top view. So we have a region which is an N-type here. This is where the emitter is, and then surrounding it is the base, and then the collector, and then the rest of the substrate here. And these are contacts being made to the emitter, contacts being made to the base, and contact being made to the collector. And these are big metal pads for eventually taking out contacts to the external world here through wires here. Okay. All right. So let's look at the operation of the bipolar transistor. So what we have already seen from PN junction is this particular fact, that when you take a PN junction, NP junction, and you forward bias it, you apply negative to the N, and this side is ground. So you're forward biasing the NP junction here. What you end up getting is two currents, an electron current and a hole current. This is the direction in which holes go, and this is the direction in which electrons go. This only shows the direction of electron flow. The current, of course, would be opposite to the direction here. So we get two components, IN and IP. And we know that each one of those current components we have seen, IN and IP, they go exponentially with voltage, QV by KT. And we've also seen that, for example, the current IN and IP, the ratios you can control by controlling the doping. If you want, for example, IP to be small, what do you have to do? If IP has to be small, what do you have to do? Say I have an IP of 0.1 ampere per centimeter square. You want it to reduce by a factor of 10. What do you have to do? Increase the doping here, right? Because this current is a minority carrier current. It depends on Ni square over Nd. So you increase the doping by a factor of 10, the current will drop by a factor of 10. If you want to increase this, this is the whole current here. If you want to increase the electron current, if I want to increase the electron current, again, I don't increase the doping here. Doping will not do anything. What I do is I decrease the doping here, because these are all minority carrier currents. So it depends on Ni square over Na. And so you decrease the doping in P region, and then this current would increase here. So anyway, by controlling the doping here and by controlling the doping here, I can control the ratio of these two currents here, IN and IP. And as I said, if you want this current to be much larger than this current, then what we do is we make this current small by making this region heavily doped. So we make it N plus. So if I make it N plus, the whole current becomes small. And if I keep a lighter doping in P, the electron current then becomes significant. So that's how I make electron current much larger than the hole current here. So I can make IN much larger than IP by simply raising doping here and keeping doping small here. All right. So when we see a bipolar transistor, what we see is two junctions here, N plus P and P and N. So what we see here is two diodes, right? NP is one diode and PN is another diode. And of course, a bipolar junction transistor is not simply two diodes back to back though. Okay, so I have one diode here and another diode here. You can't simply take two diodes, connect them up and expect a bipolar transistor action. So here is one diode and here is another diode. Two diodes are there, two independent diodes. I have forward bias one diode here. So forward bias, which means currents are flowing, significant currents are flowing, IN and IP are flowing here. And I have another diode here. This is ground, and of course, because it's reverse bias, that's why I've shown with the dotted line, the currents are very small, almost negligible here, and this component is also very small. And so we have these two diodes, independent diodes. If you short them together with a wire, it's not going to make any difference, right? Whatever current flows here, it comes here and then goes to the ground here. And whatever little current flows here, it flows between here and ground. So just connecting two external diodes back to back is not going to change anything. It's the same thing as the property of this particular diode remains the same. And the characteristics of this particular diode also remains the same. No change occurs here. Okay. It's just that these two are, you've just connected them, but it doesn't make any difference here. They remain as two independent diodes. There's no connection between them. I mean, there is a connection, but the fact that there's a lot of current flowing here doesn't affect this particular part at all, because all the current that flows here will come to the contact, will go to the ground. And similarly, whatever little current flows here will continue to flow between here. There's no alteration of the property or the characteristics of these two diodes, whether you keep them in isolation or you connect them with a wire here, right? So this is not what a bipolar transistor is. Although it has two junction diodes, but bipolar transistor is not simply two diodes externally connected with a wire. All right, so let's see how this particular transistor then works here. Okay, so I've taken a PN junction diode, right? Just turned it to 90 degrees here. So I have a diode here, N plus P here. So this is a diode here. I've made a contact here and I made a contact here. Now in this particular diode, note that I have forward biased this particular diode. I've applied negative voltage here, and ground here. So when I apply a ground here, the voltage here, so which means that the P-type, the voltage here, ground, will make all this region equal to zero bias here. All this region zero bias here, and this region would be, let's say, minus 0.7 or so. So at this junction, I have an effective voltage of, let's say, 0.7. Okay, so it's forward biased. When it's forward biased, the electrons will be injected and the holes will be injected, and the thickness of the arrows show that a lot more electrons are injected and comparatively less holes are injected here. Okay, so this is the situation when I have a PN junction diode which is forward biased. Let me take another PN junction. So I equal to, of course, total current that flows here is IN plus IP here. And because of our arrangement, IN is much larger than IP. This is much larger than this one here. Let's take another diode here. Right, another diode we have taken. This particular diode, note that it's a P and N diode here. And PN diode, we have made P ground and we have made N positive. So obviously it is reverse bias PN junction here. And in this case, the currents are, of course, the holes are, the electrons are flowing from, P to N here. So actually, if I use these arrows for electrons, so I should have drawn it, the electrons are flowing in this direction here, but the current is in this direction, so that's fine here. And then the holes are flowing from N to P. Well, the holes are flowing from N to P, so I should have reversed the direction here. Okay, so the directions are not proper. Okay, so because it's reverse bias, the holes should have been flowing from P from N to P. So the direction of the whole flow should have been here, and the electrons are flowing from N to P. So if I look at the direction should have been here. Okay, so reverse the direction. Anyway, these current components are very small. All right, so these are two independent diodes. But a bipolar transistor is what? We take this PN junction diode and take this one, and bipolar transistor, you fuse them together. It's not simply take two diodes and you interconnect them with a wire. What you do is you fuse them together. So this is what we are going to do here. Take this PN junction diode and fuse it together here. All right. Fuse it together, and now we realize when you fuse it together that the original P could serve as P for this particular diode also. And this contact, for example, I need not make a contact here. The original contact can serve as a contact for this one also. So we are fusing these two diodes and realizing that the same P can serve as P for this particular one, and the same contact can serve as a contact for that one. So when you fuse them together, this is what you end up getting. Take two PN junctions. So it's not simply two PN junctions externally connected by a wire. Two PN junctions actually fused into each other. Okay, and this is what you get here. So now realize that N plus was injecting a current here, electron current, right? And if this P region is small, these electrons which are injected here will go all the way to this particular junction here. Because this is a neutral region, so the electrons diffuse across this particular neutral region. And when they come here, what do they see? They see an electric field, depletion region. And what is the direction of the field in the depletion region? The field is in this direction here. Fields are from N to P. So field is in this direction. So the moment the electrons reach here, the field pulls the electron into the depletion region and then into the N region here. All right. So because you have fused them together and you have kept P as small, P thickness is small. So whatever electrons that you inject here, they go all the way to the N region. The whole current, of course, remains the same. The whole current is going into N plus, so nothing really happens to the whole current here. And therefore, you get something very interesting, that when you fuse them together like this, you get that although this junction is reverse biased, N and P, you can see here is a reverse bias, a very large current starts to flow through a reverse bias junction. A very large current, and the origin of the current is actually injected from here. Okay. Now you may question why, for example, let's say you have injected electron, why does it not go here? Why does it go all the way here? What are the dimensions as I go here? This is like 1000 angstrom. And what are the dimensions here? Microns. This contact could be 2-3 microns away. So this is, when you look at diffusion process, the electrons would diffuse quickly to this particular boundary here, rather than going all the way here and then eventually getting or recombining with holes and all that. Okay, so that's what happens to the electrons. All the electrons that you inject, they all end up here. They all end up here, and the field then pulls them into N, and then the electron comes here. Once the electron comes here, then of course it's an N-type region. It's like a resistor. It flows into the contact. All right, so we've ended up. So you can see here that we have connected two diodes together, but we have not connected them simply through a wire. We have fused them together. And this fusing them together is what is bringing out this linkage now. Remember earlier the two PN junction diodes were like independent. Now the two PN junction diodes are linked together. And they're linked together by this current here. Whatever current you inject here, the same current ends up flowing here. Okay, so this is the linking current here. It links the two diodes together here. And this is a current which is independent, which is fine. Okay, so now in this particular situation, so if we define collector current here, we know that and let's call this current as IN, electron current component, and let's call this IP. So collector current for us is going to be basically equal to IN. IC will be equal to IN because there's no other current, because note that this is reverse bias and the current of this particular junction is very small. By itself, the intrinsic current is very small. Right? It's a reverse bias junction. The current that comes in from here is the important current here. Right? So IC then is basically equal to this IN. All right. And if we look at IE, IE will be of course made up of both these components here. So it will be equal to IN plus IP. That's the emitter current. This and this both are flowing here. And if we look at the base current here, base current, where is it coming from? note that holes are being injected from P to N. So base has to supply those holes here. Every time a hole goes into an N plus, you leave a vacancy for a hole here, and then current comes in to fill that particular hole which is lost here. So base current that you see here, it supplies these holes here. And we are saying that all the electrons go into the collector, but some may recombine here. Very, very small fraction may recombine here. And therefore, when an electron recombines with a hole, so one hole is lost. So the base current has to supply the hole which is lost also, right? But base current is primarily equal to this current here, IP. So that's the relationship between the different currents that you see here. Emitter current made up of both of them. Base current made up of the holes which are injected, and collector current, of course, is this IN. And we note that the collector current divided by base current is what we call as a current gain. So IC is simply equal to IN and IB equal to IP here. So IC by IB is IN by IP, and we know that IN by IP we can make large simply by controlling the doping here. So doping allows us to make this particular ratio large here. Now the reason why we are calling it is so one way of looking at a bipolar transistor is the following, that you change the emitter voltage, and as you change the emitter voltage, what happens? This, for example, if you increase the emitter voltage, this current will increase, this current will increase, and therefore this current eventually flows here, and thereby you increase the collector current. So as you change the emitter base voltage, what happens to the collector current? Increases. Increase the emitter base voltage and the collector current will increase. And what will be the relationship between them? If you increase the emitter base voltage, how will this current increase? Exponentially, right? Each one of these currents are exponential with voltage. So this current increases exponentially, and therefore this current increases exponentially. What about the base current? The base current is made up of this term. This current also increases exponentially. So as you change the emitter base voltage, both base current and collector current both increase exponentially. But the ratio of the two, IC and IB, is the ratio of IN and IP, and we have seen that both of them increase exponentially. So the voltage parts cancel out, and IC by IB is equal to IN by IP, and you get a constant. You get a constant, and we call that particular constant as the current gain of the transistor. So one way of looking, as I said, one way of looking upon a bipolar transistor is that you are controlling the collector current flowing here, by the applied base emitter voltage. As you change the base emitter voltage, you change the current. So you're controlling collector current through base emitter voltage. Another way of looking upon bipolar transistor is you're controlling the collector current by base current. So you don't apply, for example, a base emitter voltage, let's say. You keep this as, for example, I could keep this as ground. And what I do is, at the base, I put in a current source. I put in a current source, some amount of current source IB. What will this current source do? If I inject a current source, what it will end up do is forward biasing this particular junction, because a current has to flow. And where will this current flow? If I inject a current, this current has to flow like this here. And what it does is it forward biases this junction here. And as it forward biases if this current source will forward bias this junction. So as this current flows, this also has to flow, because the two are related together. And therefore you end up getting a collector current. So in that case, what are you doing? You're controlling the collector current through a base current. So you inject base current, and thereby you control the collector current. So the controlling variable becomes the base current. If you increase the base current, the collector current increases. If you decrease it, the collector current decreases here. And therefore, that's why this gain becomes important. You can use a very small current here to control a very large current here. Right? So that's the importance of the current gain that comes in. Using a small variable, you can control a large variable here. Okay? So you can see now that I can represent my transistor in this particular manner here. Let's see if this diagram makes sense here. So transistor, then under this configuration, note that I have a junction here, I have a diode, so I have a diode here. No problem. And I have a diode here, so I've drawn a diode here. So that's the other diode. But then we have, as I said, we have fused these two diodes together. So what is happening is the following. In this diode, the total current that is flowing is, let's say, IF. What is the total current IF is what? This current, IN, plus this current IP, right? That's the total current flowing here. Now, what happens is, note that when we have fused them together, a part of this current IF. IF is made up of these two. A part of IF. Which part? This part. This part flows through this junction also. And how do I represent this? I represent this by this source here, by this current source here. So note, a part of this particular current IF that you see here, alpha F times IF, flows in this particular junction, right? So, and of course, I have this usual reverse bias diode here. So my bipolar transistor under this configuration is this particular diode as usual, no problem. I have this diode as usual, no problem. But then note that because we have fused the two junctions together, there is a linking current here. Whatever current flows here in this particular one, a part of it, which part? The IN part flows through this particular junction here, and you get this current source here, dependent current source. So that's the key difference between a bipolar transistor and two diodes fused together. Two diodes simply connected together. If I take two diodes connected together, I'll get this and this, that's it. Now, because of this arrangement here, you get this current here. So this is the key current here. This is where all the bipolar action is. That you have a current injected from at one junction, which flows into the other junction here. So this, so the whole story is with this particular current source here, dependent current source, voltage. I mean current dependent current source here. Whatever current flows here, a part flows here. So that is the key part here. Okay, so my bipolar transistor under this configuration can be represented by a diagram like this here. Another way that I can represent it is in this form. So this is, we are using base as a sort of common terminal. We are writing emitter here and collector here. Now we have used emitter as a common terminal. So we are saying between base and emitter, there is a diode, which is fine. Between base and emitter, there's a diode. And note that this particular diode doesn't conduct because it's reverse bias, so I can remove it also. So between collector and emitter, this shows that between here and here there is alpha FIF, and between here and here there is IF, right? So between the collector and emitter, I can put a current source of this kind here, right? So this is the current source. So I can take the same circuit and I can redraw it in these terms. And so what it shows is that between base and emitter there is a current, and between collector and emitter there is another voltage dependent current source here. So I can rearrange the circuit in this particular form, right? So now it's beginning to look like a transistor, because remember, if I use base emitter as an input port and collector emitter as an output port, what we were looking for in a transistor is that the base emitter voltage should be able to control collector emitter voltage here. And this is what we find here. The base emitter voltage should be able to control collector current here. So this is what we find. As we change the base emitter voltage, the collector current, which is this current here that you see here, is very sensitive to base emitter voltage here. And as I change my collector voltage here, as I change my collector voltage here, note that this current is not affected. This current that you see here, this current is what we are drawing here, is simply not affected by the collector voltage here. Because as you make the base more reverse bias, what does it do? Well, all it does is it increases the depletion region width, it increases the electric field, and this is not what is determining the current. The current is coming from here. The current is determined by this current here. So current is determined by voltage across this junction, not across this junction. This junction simply collects whatever is sent to it. All the electrons that come to it, it just collects it. And it's an efficient collector anyway. So whether you apply -1 volt, -2 volt, -5 volt, +1 volt, +2 volt, or whatever, it doesn't really matter. Okay. So as I change the voltage here, it's not going to change this particular current. And therefore, it doesn't change this current here. So that's where the transistor action is. I have a current flowing between these two terminals, which is very sensitive to voltage applied here, but is not sensitive to voltage applied here. And that's what we were looking for, right? We don't. In an ideal transistor, we had shown this as open circuit. It's not an open circuit in our case, and we had shown that the current between here and here linearly varies with voltage here. In our case, the current that flows here doesn't vary linearly base emitter voltage. It varies exponentially here. But it shows the basic feature of current being very sensitive to voltage here and not sensitive to the applied voltage here. So that's where the transistor action takes place. And so the key variable then is this current here. This is the current which links this junction and this junction together, which is described by, which gives rise to a current source here, which gives rise to a current source here. So that is the key part. Okay. All right. So there are various ways of representing it. For example, in this case, we have represented it as a diode, and we have said that the current source is a voltage dependent current source here. Well, we can also write it as current dependent current source here. We can write, because note that we have already shown that the collector current that flows here is related to base current through beta times IB. So we can represent it not in terms of base emitter voltage, but in terms of IB here. Okay. So beta then is, we have already seen IC by IB. We'll see these things later on. Okay. So here is, here is one view of a transistor with base emitter junction forward biased and collector base junction reverse biased, right? So two diodes and a linking current, which is here. Now suppose this is what we call as the forward active mode. Base emitter junction forward biased, base collector junction reverse biased. Now suppose I do the other one. Base emitter junction reverse biased, this is reverse biased, and collector base junction forward biased. So same thing happens. Now this junction is forward biased, note. This is injecting electrons, and whatever electrons are injected, they will go here into this particular region. And of course, the base is injecting holes here. So same thing happens, except that the role of emitter and base are role of emitter and collector are interchanged. So what we get is a circuit like this. Two diodes again, as usual. Two diodes here. This is the diode which is forward biased now. So as it is forward biased, a current IR flows, and a fraction of this particular current flows in this particular junction here, right? This red one here, it flows across this particular junction here. So this current that you see here is what is coming here. And of course, it's a reverse bias diode, its own current would be very small. So here is a forward active mode, and here is a reverse active mode. This is when this junction is forward biased, and this is reverse bias. In this case, this is forward bias, and this is reverse bias. And we get a circuit like this. Now you can think of a more general case. A more general case would be what? So the idea that is happening is the following. When you forward bias a junction, a current flows here. A part of this current flows through the other junction. That's the transistor action, alpha F times IF. If you forward bias this junction here, a part of this current flows across this. So the two junctions are linked together. Whatever happens in one junction, current happens in one junction, a fraction flows here. Whatever current flows in this junction, a fraction flows here. Now if you forward bias in general both the junctions here, you can expect the complete model to look like this, right? So so some current flows here, IF, in this, a fraction flows through the other junction, alpha F IF. Some current IR flows through this particular diode, a fraction alpha R IR flows through this particular one. So these are the linking currents here. And these are the linking currents here. IF causes alpha F IF to flow. IR here causes alpha R IR to flow. Why alpha and alpha? Because note that the current which flows again through this junction, this part is the linking current. This part of the current flows through this one also. This part doesn't flow. Okay, so that's why we have the entire current with this particular junction doesn't flow through this. Only this part flows here. And that's why we have an alpha. And alpha, of course, will be less than 1. Okay. So this is what we call as a Ebers-Moll model for a bipolar junction transistor here. This is the a general view of how a bipolar transistor looks under arbitrary bias condition here. If I go to forward active mode, I will go here. If I go to reverse active mode, I will go here. And whichever other mode I can derive from this particular model here. So right now what we have done is we have derived this Ebers-Moll model through more qualitative means by saying this is how in forward active it looks, this is how it looks in reverse active, and then we combine them together and we say this is how Ebers-Moll model looks here. What we are going to do next is, well, not Ebers-Moll model, but Ebers-Moll model. Okay. All right. All right, so the next thing that we are going to do is mathematically derive this here. Okay. So what we are going to do is the following, and out of all this derivation, you will also get expression for current gain, and you will get, for example, how to get the transistor characteristics in saturation and other things as well. Okay. So what we are going to do is the following. We'll assume a 1D transistor structure with uniform doping in all the regions. Uniform doping in N plus, emitter, base, and collector. All right, so that's one thing. To keep our derivation simple, we'll assume narrow base width. Narrow base width means so that carrier recombination within base can be neglected. Remember what we said was if I go to a transistor and I inject an electron comes into P and the electron can recombine. But the average distance an electron travels before recombining is the diffusion length. And diffusion length is usually large. So what happens is if I keep my base thickness much smaller than diffusion length, the carriers are not going to recombine much. Okay, so that's the idea here. So narrow base width so that carrier recombination within base can be neglected. We'll assume low level injection condition. We'll assume that there's no recombination within depletion region. So I'm going to derive a model which is valid for reasonably higher currents, because we know that at very low currents, recombination within the depletion regions become important, but I'm not going to look at that. And of course, I'm going to look at steady state or DC bias condition. I'm not looking at transient. So a series of assumptions are being made to simplify the derivation of the Ebers-Moll model here. Okay. All right. So this is the picture that we have. All right. This is the transistor. Uniform doping here. Uniform doping here. Uniform doping here. The other thing is uniform base thickness very small, so that very little recombination. Okay. All right. Now note, let's see if we can write it down. The emitter current at this point will be equal to, this is the direction that one has just assumed. The emitter current may actually flow in or flow out, depends on the bias conditions here. So that's only a indicated direction. Is equal to IPX1 plus INX2 here. Say you forward bias the emitter base junction. The current, what will happen is holes will flow here. This is my hole current. And this is my electron current. Note that electrons will be injected here, but the direction of the current will be here. So IPX1 plus INX2. We have already seen that current in the PN junction, you can calculate by looking at minority carrier currents. Minority carrier current here, which is IPX1, and minority carrier current here, which is INX2. If you sum them up, you get the net current flowing through the junction here, and minus IE because of the direction that we've assumed. So minus IE is IPX1 plus INX2. Similarly, this current here, we assume that this is, let's say the whole current flows here. Electron current, we have assumed it in this direction only, in this case, because note that whatever current flows will be similar in this region here. So minus IC will be equal to IPX4 minus INX3, right? Minus INX3. Because note I've written here minus IC. Again, the collector current, the net current flowing at this particular junction would be sum of these two. And because of the direction that I've assumed, I have to put minus INX. So that's IC. Base is what? Base current is equal to IPX1. Base current is what? Is supplying this current here and is supplying this current here. So base is IPX1 plus IPX4. Right? So these are all the currents that you see here. IE, IC, and IB. All the currents are there. Does it violate anything? It implicitly assumes something, right? Because the sum of IE plus IB plus IC should be? Kirchhoff's current law should hold, right? All the currents going in. So IE plus IB plus IC should be equal to 0. So if I put IE plus IC plus IB, what do I get? I will not get 0. I will get INX2 minus INX3, right? I will get that. So implicitly, what if I assume that this current is same as this current here? What does this represent? Electron current. So what we are saying is whatever electron current is here, the same is the electron current here. And why? Because there's no recombination. Right? So there's an implicit assumption when I write this is that these two currents are the same here. INX3 and INX2 are the same. Because whatever electrons coming to the base, they don't recombine, so the same must be at the other end also. Okay? Let's look at that in more detail here. This part here. This is the key current here. This is the current here which links the two p-n junctions together here, the electron current here. So we have said that we are assuming narrow base width so that carrier recombination within base can be neglected. So if I look at the base and I look at the electron density in the base and I've written down continuity equation. Since we are talking about DC, so I'm going to put del N by del T 0. Then what am I assuming? There's no generation. I'm not shining light or anything, so Gn is 0. And what am I assuming? Carrier recombination can be neglected. Rn is also 0. So what am I left with? I'm left with del, this is in terms of current density, I can write it in terms of current also. Del In by del x is 0. That's what my continuity equation tells me. In is a constant. And that's why INX2 is INX3. Whatever is the current at one end, the same current must be at the other end here. Why? It's all coming from, if I assume, negligible recombination within the base. Continuity equation is telling me that these two have to be the same. Okay? So, that's fine. The other thing is, so what we have said is, this current is the same as this current. The two currents, INX3 and INX2 are the same. The next thing is, what are these currents here? If they are the same, what is that current here? Now, if you look at, we have said that del In by del x is the same, so same current is flowing. But then this current that we are talking about is electron current. Electron current in a p region. That's minority carrier current. And remember what we had shown you also, minority carrier current is, in a p-n junction, diffusive. There's very little drift component. So this is what we're going to write here. If it is diffusive, In I can write as Q times dn times del N by del x, and area we've added because, current density multiplied by area. So we have this In equal to Qa dn del N by del x. So this current here can be written in this form. Now can you see something else also? In is what? Throughout this region, In is what? Constant. If this is constant, Qa dn of course is a constant. It implies del N by del x is? Del N by del x is constant. Which means what? How is the electron density changing in the base? Linearly. Electron density in the base is changing linearly. It has to change linearly, and therefore we can write as the electron current in the base as Qa dn del N by del x. Well,